now.
Hello guys, you're all on spring break right now, and Mr. Cullen and I are here working hard at the Mother Eye to give you guys an in-class demo on the control system for a motor. And so here's our motor right here, and you can see the oscilloscope. I have 2 channels being recorded on the oscilloscope right now. This yellow one is the voltage. It's a square wave, and it's just positive, negative, positive, negative. It just keeps going back and forth. So what that is a step input, and we've had step input in class a lot for our different motors. And so what this green line is, that shows the position of the motor at any given time. And so if I take, right now I have this wire disconnected so that nothing's happening with it. But if I take this thing and put it into the input, and let's see, where did I have that? There we go. Okay, so you can see the motor sort of responding there. It goes back and forth and back and forth, and you can see the motor response here on the oscilloscope. And of course it's not a perfectly square wave because the motor is a mechanical system and it doesn't respond instantaneously. It goes up and down. So if I just took this control board here, and I've got feedback on it, if I take the feedback off of it, we can see that the motor just rotates one direction when the voltage is positive to it, and it rotates the other direction when the voltage is negative. So it never really stops in one place. The line is just flat line because the motor is always moving. But now I'll hook up this feedback again to it, and right now I just have proportional gain hooked to it. You can see I have 3 little knobs on this board here. This is the proportional knob, and then it's got an integral knob and a derivative knob. So you can put in varying amounts of proportional, integral, and derivative feedback to this thing. And right now we can look at this motor and see that it is probably an overdamped system, right? Now we know from our welding robot example in class that if I put more proportional feedback on this thing, eventually it'll start to overshoot. So right now I have it at about the lowest setting on proportional control, and I'm going to start increasing the amount of proportional control. And now you can see that we're starting to get some overshoot on it, some oscillations, because we start getting those imaginary roots from our characteristic equation. It's a second order system. I'll put in a little more proportional control, and we can see it overshoots even more. It oscillates even more at a higher frequency. We're not getting a faster settling time out of it, but we're just increasing the frequency there. So if I take this thing all the way back to the lowest setting again, and you might not be able to see this on video, but one thing you can do with this oscilloscope is, and you may remember this from instrumentation lab, when we pulled the cord on the motor in the back of the instrumentation lab. In fact, we're in the instrumentation lab right now, and I'm looking at the motor back there. We were able to use little cursors to check out the high and low voltage on that device. So we can do the same thing here. This oscilloscope has cursors also. If I can find them. Okay, so right there are the cursors. And I can move the cursors back and forth. Whoops, my whole thing went away. All right, there we are again. So again, you probably can't see the cursors there, but if I've recorded it, and if we look up here on the board, we can see we've got a homework problem that has to do with this control system right here. This is our control system for the motor. So you can see that this 1 over JS plus C, that's what we'd have for a system where we're concerned about the speed of the motor. And so the input going into this thing would be torque, and then the 1 over JS plus C, the output of that would be the speed of the motor. And then this 1 over S here is another integrator, as we know from many times in class. So the output of that is theta. If you integrate the shaft speed, you get the shaft position. And then we're feeding that back into our control system right here, where we have derivative, proportional, and integral control. And we have this K value for it. And basically I was just adjusting this KP, and we saw that it went into overshoot. And so we can see here that with no PID compensator, we set the proportional gain to 0.2, which is about the lowest you can have it. And we had overdamped, and by moving those cursors, we can see that we got like 0.94 seconds settling time. Then we increased the proportional gain, and we got probably what was critically damped. It's a little tough to tell from the oscilloscope if it's exactly critical damp, but it sped up the settling time to 0.82 seconds. So what we have to do for this homework problem is design a PID control system to bring the settling time down to 0.4 seconds with no oscillations. And so that is your job on this problem. And it's basically using this real system over here that we looked at and just changing those settings on the knobs. And it should give us these design criteria for our output. And that is the end of the demonstration.